All right, the fun begins. This is the first video in BC Calculus on sequences. This first section, and even really this first little sequences and series unit, is going to be like sequences and series light. It's not overly intense. It should hopefully be stuff that makes sense to you because even though you haven't necessarily talked about it in this context before, you have seen these types of sequences and things before, a good bit of them. So, just to refresh your memory, a sequence is any list of numbers that are written in a particular explicit order. So, for example, 2, 5, 8, 11, 14. That's a sequence. They're all written in order, and their particular order is that we are adding 3 every time. Okay? The individual numbers make up the terms of the sequence. So 2, 5, 8, 11, 14, those are all terms. A sub n is the nth term of the sequence. So for example, I would say that a sub 3 is 8. The third term of the sequence is 8. Okay? A sequence can also be thought of as a function. So the domain would be the set of positive integers. So that's basically the term number. So term number 1, 2, 3, 4, 5. And then the range are the actual terms in the sequence. 2, 5, 8, 11, 14. Now, in previous math classes, and I'm talking like way, way previous, like middle school even math classes, you would get a table like this, and the teacher would ask you, come up with a formula or an equation to model this data. Like we can see that the pattern is to add 3 to each of those terms, but now if I want it to be in terms of a function where this is like my x and this is my f of x, it requires a little bit more thought because you're trying to figure out, well, if x is 1, what could I do to it mathematically to turn it into a 2? And could I do that same thing to the number 2 to turn it into a 5? And could I do the same thing to the number 3 to turn it into 8? And so on and so forth. That's called an explicit function for a sequence. And we're going to come to that in just a couple of minutes. Before we come back to this, though, I want to define 2 particular types of sequences. You have a finite sequence in which the domain is finite. That means it ends. So, for example, 2, 5, 8, 11, 14 is finite because it ends at 14. An infinite sequence would be 2, 5, 8, 11, 14, ... And that tells us that we would continue that pattern of adding 3 forever and for always. These are the types of sequences we are primarily going to be focusing on in this course, are ones that do not ever end. So, an explicit function for a sequence is where each term can be found discretely in relation to what term number it is. So I could plug in, if I want term number 5, I would plug 5 into a function, and it would spit out whatever the value of that term is. So if we want to go back to these particular values here, take a minute and kind of think about what could I do to that x value to turn it into that f of x value. Or we really would think about this more as this is n and this is a sub n. We don't really use them so much in terms of function notation. As with sequence notation, it's usually n and a sub n. So what could I do to n to turn it into a sub n? So I notice that each of those n values, to get to the a sub n value, I could double it. So I could double my n value. That would give me a number 2 plus n minus 1. Because if all I did was double my n value, that wouldn't work the next time around. That would get me to 4, but I would need to add 1 more than that to get to 5. And then here, 2 times 3 would get me to 6, plus 2 more would get me to 8. 2 times 4 would get me to 8, plus 3 more would get me to 11. 2 times 5 would get me to 10, plus 4 more would get me to 14. So that formula is that a sub n is 2n plus n minus 1, or 3n minus 1. So the explicit function for this sequence is a sub n equals 3n minus 1. Now, a recursive function is where each term can be found by relating it back to the term that came before it. So looking back at this one, that's really easy. All I do is I add 3 to the previous term. So that would be to say a sub n equals the previous term, so that would be a sub n minus 1 plus 3. Now, not only can you specify a recursive function, but you also have to give the starting term value. So you have to have a number to start at, because you don't know what to add 3 onto until you know where to start. So a sub 1 would be 2, and then the pattern is to add 3 onto the previous a sub n term. But again, we tend to deal more with explicit functions than with recursive functions. All right, so here we are given an explicit function for a sequence b sub n, and they want us to find the first 6 terms as well as the 100th term of the sequence. So that's why explicit is so much better than recursive. With explicit, you could find any term number you want by simply plugging that term number in. So the 100th term, to get it, all I have to do is substitute 100 into my explicit function. To get the first 6 terms, probably best if we just put it all in a list. So the first term would be the first term. So if we substitute 1 into n over 1 minus 2n, we would end up with negative 1. And then the second term, if we substitute 2 into that, we end up with negative 2/3. And so on and so forth. And then lastly, we could do the same thing with 100. If we substitute 100 into here, we get negative 100 over 199. And you could just leave all of your information contained in that table right there. Now, I did give you the directions in here for how to graph explicit and recursive formulas for sequences. You do need to change the mode of your calculator and just follow the directions on here. I'm not going to take the time to graph one because honestly, we don't really ever look at the graphs. Perfectly honest with you. But if you wanted to ever look at a graph for a recursive or an explicit sequence, this is how you would go about graphing it. So that's explicit, and then the recursive is further along in your notes. So example 2 says to find the first 4 terms and the 8th term for the sequence where we're given the recursive formula. So this is a d sub n function. So we have n and we have d sub n, and they wanted the first 4 terms. Well, they gave us the first term, it's 25. And the formula says d sub n plus 1 equals d sub n minus 5. So the number that came before it, minus 5. So 25 minus 5 would give me 20, and then 15, and then 10. Now, they also asked for the 8th term. So you could either try to figure out the explicit function at this point, and then plug 8 into it, or you could just continue your pattern until you got to the 8th term. Since it is 8, it probably would be faster just to do that unless the explicit formula is just kind of popping out at you. Now, if this was the 100th they were asking for, then I would definitely want to take time right now and find the explicit function, but I don't need to do that. So if I keep subtracting, 5 would be 5, 6 would be 0, 7 would be negative 5, and so 8 would be negative 10. Okay? And then, like I said, there's the directions for graphing a recursive sequence in your calculator. The next thing we're going to talk about is a limit of a sequence. So, back to limits, yes, but it's always going to be the limit as n approaches infinity. So basically, if we kept writing out in terms over, like on and on and on forever till the one infinite term of the sequence, would our terms start to approach a common value? Like, would they start to get smaller? Would they all start to approach a particular number, kind of like a horizontal asymptote? So this is the definition for it. It just says the sequence a sub n has a limit L as n approaches infinity if, given any positive number epsilon, there is a positive number m such that for all n is greater than m, we have the absolute value of a sub n minus the limit is less than epsilon. All it means is, does it have a limit as n approaches infinity? Then we say that it converges to that limit value. And if they don't have a limit, then we say that those sequences diverge. So I'm going to show you an example of each so that you can kind of see what I'm talking about. So a sequence that converges would be 1, 1/2, 1/4, 1/8. What can you see that that sequence is doing? It's continuously dividing the denominator by 2. So that denominator is going to continue to get smaller and smaller and smaller and smaller. It's never going to cross over into the negative land. So that whole sequence is going to converge to 0. So we would say the limit as n approaches infinity for our sequence that doesn't have a name, we'll just call it a sub n, is 0. Now a sequence that diverges would be one like 1, 3, 5, 7, 9, so on and so forth. That's all my odd numbers. It's just going to continue to grow and grow and grow and grow all the way up to infinity. Now, a limit for a sequence cannot be infinity. So we would say that it diverges. Okay? One helpful thing is that if you have an explicit function for your sequence, and if that explicit function has a limit as x approaches infinity, then that's also the limit for your sequence. For example, if we look at a sub n equals 1/2 to the n minus 1. If I do the limit as n goes to infinity of 1/2 to the n minus 1, that's the limit as n goes to infinity of 1 to the n minus 1 over 2 to the n minus 1. Now it doesn't really matter what the top is going to be a 1. The bottom is going to be 2 to the infinity minus 1, or infinity, which is 0. So, therefore, a sub n converges to 0. Another example, what if we have b sub n equals 2n minus 1? Well, the limit as n approaches infinity for 2n minus 1 is 2 infinity minus 1. That's infinity. Therefore, b sub n diverges. Okay? All right, so we're going to end this first video on example 3 here, where we are given an explicit formula for a sequence, and we're to determine whether or not that sequence converges or diverges. If it does converge, then we want to find what it converges to, what its limit is. So I want you to pause the video for a minute and see if you can determine whether or not this sequence would converge or diverge. All right, so since it was a limit as n goes to infinity, you can use n behavior model, and you just end up with 2 for your limit. So that means that this sequence, if I was to write out all my terms for it, or a good bit of terms for it, I would see that those values of the terms start to approach a value, or exactly equal a value, of 2. So that wraps up the first video on sequences.